All right, so what I'd like to do is I'd like to look at a bar magnet and figure out what its magnetic moment is, knowing its saturation magnetization, which is 10 to the 6th amps per meter. Okay, so how do we do that? Well, the magnetic moment is equal to the volume times the magnetization. And we said this bar magnet has a length of 10 centimeters and an end cap area of 1 square centimeter. So that means the volume is 10 centimeters, which is 0.1 meters, times 10 square centimeters, which is 10 to the minus 4 meters squared, 10 to the minus 2 for each centimeter. And then we have our saturation magnetization of 10 to the 6th amps per meter. And that's going to give us 10 to the minus 5 times 10 to the 6th amps meters squared, because one of these meters cancels there, so we have an amp and a meter squared left over. So that's 10 amps meters squared. So that is the magnetic moment of the bar magnet. And then, sometimes this is quoted in Tesla. So fields are in Tesla. There are reasons why you might want to use Tesla over amps per meters that we're not going to get into in this class, because they really have to do with magnetic fields in materials. But a lot of times these things will be quoted in Tesla, and to convert from amps per meter to Tesla, you have to multiply by mu naught. So basically, if we want to get this in terms of Tesla, we need to take mu naught times m. And let's see, that means we have mu naught, which is 1.256 times 10 to the minus 6 Tesla over amps per meter, okay, times, in this case, 10 amps meters squared. Okay, so that just means we have 12.6 times 10 to the minus 6. We get rid of an ampere. We have an extra meter, so 1 over m is equal to m, so that gives us Tesla meters squared. So that's 12.6 microtesla meters cubed, meters cubed. Okay, so that seems to be reasonably straightforward. The moment is just the volume times the magnetization, right? So we've got our guy as a magnetization m. The dipole moment, m, is just equal to the volume times the magnetization. So we did that first, and then we just did a conversion. This is how, if you see something quoted in Tesla and you care about amps per meters, which you may or may not do, but you might have to compare two things, so that's a useful thing. And we're going to be using this mu naught guy over and over and over again, the permeability of free space. So we'll see that that has to do with converting from a current basically to a field. That's the relationship between the current and the field in a way. So that is more or less what we need for this particular guy. So next we'll go on and do something a little more complicated. Not too much more complicated, but a little more complicated.